We will consider a few more examples of finding equivalent capacitance and where there is no simple series parallel connection. So we're going to find a technique. We already found a technique, but we're just going to practice a bit. So this is our system of capacitors connected between A and B. There are two junctions, extra junctions between A and B. I have seen that if the capacitor did not exist, it would be a simple connection. But with that capacitor added, it makes it all messy. Let's say this capacitor C, 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 and this is 2C and 2C. You assume a potential difference, say this is 0 and this is V, and solve for this is the potential difference applied between A and B. We would like to find how much charge flows in through the terminal A or leaves through terminal B. Let this be V1, and before assuming a label here, we'll ask a simple question. What do I know about how the charge would flow? There is symmetry here and we could exploit that. The charge that flows this way should be equal to the charge that flows back to B through this path. Charge that flows through 2C here, will come through this 2C to the terminal B, which means the potential difference across C's must be equal and potential difference across 2C's must be equal. So if we assume this to be V1, the potential difference across this 2C is V1, this 2C is also V1, so potential difference is V1. So, and if this potential is V minus V1 across this capacitor, it must be V minus V1 across this. So we don't need a new label here, we'll write this as V minus V1. That's the potential here, assumed in terms of the already assumed label. We don't need a V2 here. And what do? We assume labels for potentials and write equations for charges. Like if I isolate this set of conductors, there are no wires crossing that boundary, that dotted line that we've drawn. So no charge flows onto these conductors from outside. Sum total of charge in that they must be 0. This V1 will assume V1 is less than V, so this will be negative plate. And the charge in that will be minus C into V minus V1. And the charge on this is 0 and this is V1, so this potential difference is V1, 2C V1, right? So that's plus 2C V1. And this one will be this V minus V1 and this V1. So the potential difference across this will be V1 minus V minus V1. That is V1 minus V minus V1. That is V minus 2V1, right? V1 minus V minus V1. That is 2V1 minus V. So that's plus C into 2V1 minus V. That will be equal to 0. And then I will solve for V1 in terms of V. We'll treat V as a known quantity and solve for V1 in terms of V. We have plus V1 here, plus 2V1 here, plus 2V1 here, that's 5V1. And this is minus V, C has gone away, and this is minus V, so that is minus 2V, going to the other side it becomes 2V. So V1 is 2V by 5. V1 is 2V by 5, this is 3V by 5 and this is 2V by 5, right? This is V1, 2V by 5, this is 3V, this had a higher potential, this plate is positive, but that really doesn't matter. We assumed and we followed this assumption. We assumed that V1 is more than V minus V1 and we assumed the charge here is positive. That doesn't affect your calculation. Once you got this, what is C effective? C effective would be charge that is flown through terminal A or the charge that is flown out through terminal B. So whatever charge enters A leaves through B, and B is a little more convenient because this 0 potential here. What is the charge on this now? Minus 2CV1. That's because 2CV1 is left through this path. That is 2CV1 through this, and then this is V minus V1, so this is C minus C into V minus V1, so that is because C into V minus V1 is left that path, that by V. Now that you know V1 in terms of V, you know V1 in terms of V, right? So this is 2V by 5, so V gets cancelled, so we just will put the numbers there. When we put V1 in terms of V, V gets cancelled, so we'll put just the number there, 2 by 5, that is 4C by 5, 4C by 5, and this is V minus V1, that will be 3V by 5, so V goes away, plus 3C by 5 by V. And what does that give us? This is 7, V has gone away, sorry. That's the capacitance, 7C by 5. Done. Let's assume charges instead, and then write a rule for potentials. Like when you apply a potential difference between A and B, we're not assuming a label for potentials. Let a charge Q flow through this terminal, splitting as Q1 and Q2. So charge flowing in is Q1 plus Q2. Q1 has gone this way, Q2 has gone this way. And if Q2 has gone this way, Q2 must come from here, so this also is Q2. And if Q1 has gone this way, our argument was there is symmetry here, and this is what we expect. So the charge on these two C's is same, and this is same, 2C, 2C, Q2, Q2, and this we'll find out. Right, if of Q1, now let's say Q1 has left this plate, this is minus Q1, Q1 has left this plate, and if Q2 has gone there, well, what we'll have will be Q1 minus Q2 here, right? Q1 has left this plate, of that Q2 has gone this way, what is left has gone this way, that's Q1 minus Q2. We're assuming that, well, Q2 is less than Q1, and that doesn't make a difference. Now, what do? We write a rule for potentials. When we assume labels for potentials, we'll write a rule for charges. Charge in this set of conductors was 0, we said. Now, we'll write a rule for potentials. That is, when you go around a loop, the potential difference must add up to 0. Let's start from here and go along this path. There's a drop in potential of Q2 by 2C. Drop, we'll take it as negative because this is positive plate and you're going to the negative plate, so there's a decrease in potential as you go there. This is all a conductor, no change in potential. And here we're going to the positive plate, that is a raise of Q1 minus Q2 by, see, there's a raise, positive sign. This could as well be Q2 is greater than Q1, and this could be negative. That will be taken care of by, well, the equations. And this one is, when you go this way, it's an increase again of Q1 by C. This Q1, so potential increases as you go from negative to positive plate. This should be adding up to 0 because we are back to the starting point. Now we'll get Q1 in terms of Q2. C gets eliminated. This is minus Q2 by 2 and this is minus Q2, that is minus 3Q2 by 2. Goes to the other side. This is 3Q2 by 2 and this is 2Q1. So what have we got here? Q1 in terms of Q2. This is 3Q2 by 4. Now let's calculate the equivalent capacitance, and that would be, C effect would be charge that is flown in from A to B, that's Q1 plus Q2. Q1 is 3Q2 by 4, Q1 plus Q2 by potential difference P. We can express that in terms of Q1 and Q2. This is Q1 by C, potential difference between A and B. This is a decrease of potential Q1 by C, and this is Q2 by 2C. Q2 is 4Q1 by 3. So plus 4Q1 by 3, this is Q2 is 4Q1 by 3, right? And there is 2C there. So 2 and 2, 4Q1 by 3, 6C. So this will give us, Q1 gets eliminated, right? Q1 gets eliminated, and sorry, I put that wrong. I'll have to replace Q1. So this is potential difference of Q1 by C here. Q1 is this, 3Q2 by 4C, plus this is Q2 by 2C. When you go this way, there's a drop in potential across this capacitor, that's Q2 by 2C. As you can see, Q2 gets eliminated and you're left with this is 1 plus 3 by 4 plus 1, that's 7 by 4, right? 7 by 4, and this is C goes up. So let's deal with number. This 3 by 4 plus 1 by 2, that will be 4, and this is 4, this is right. So this is 3 plus, that will be 2, 2, so 3 plus 2. So 4 gets cancelled, and then you have 7C by 5. That's the equivalent capacitance. Well, you choose your way, but this is a little more tedious compared to say assuming potentials. There is just one equation there, simple equation, but this too is fine, whichever you like. So assume a potential label for potentials and write a rule for charges. What was that rule? Sum total of interconnected conductors would be 0. That's all by induction that charges appeared. And if you assume a labels for charges, you write a rule for the potential differences. Algebraic sum of potential difference in a closed path must be 0. Right? Let's use the knowledge of series parallel arrangement of capacitors in doing some interesting problems. Like for example, we have a capacitor, plate's area is A and gap is D. This capacitor, the capacitance would be epsilon 0 A by D. Now imagine a thin metal plate here, anywhere in the gap, parallel to the plates. So what will be the capacitance of the system now? There are 3 conductors, right? Earlier there was just one plate, another plate. Now we have another plate, thin plate, idealized thin plate, 0 thickness. Now one way of seeing this could be, now you saw this in terms of the field earlier. Now we're going to see it as what? We have a charge flowing in here, inducing a charge on this surface. This is sum total of the charge, and this must be 0. There will be negative charge on this, and that will induce a positive charge here, and negative charge leaves, positive charge leaves through this, making it negative. So Q here, minus Q here, plus Q here, and minus Q here. Just like a series capacitor, right? You can also see the introduction of this plate has not affected the field. Field lines terminate on the top surface and begin again on the bottom surface. So if field was earlier E in the air gap, it will remain same E in the air gap now. Field will be 0 in the metal, and that we idealized as 0 thickness. So if this is a gap of D1 and field lines will be like this, from this plate to this plate, normal to the plates. Potential difference is ED1, and this will be ED2. E into D1 plus D2, and D1 plus D2 is D. So potential difference is not affected by the introduction of this plate. The capacitance of this portion is epsilon 0 A by D1, and this is epsilon 0 A by D2, and these two are in series. So 1 by C will be 1 by C1. C1 is epsilon 0 A by D1, right? That will be epsilon 0 A by D1 plus 1 by C2, epsilon 0 A by D2. So this is D1 plus D2 by epsilon 0 A, and so you can see C is epsilon 0 A by D1 plus D2, but that's D because this idealized 0 thickness. What we are saying is we can see the capacitor's number of series capacitor. If you imagine such plates, this introduction of this plate has not affected the capacity. This will serve a useful purpose for us. Alternately, you could imagine say a small portion like this, well, is in parallel with the other similar portion by its side. Now that's because the potential of this and every potential of every pair of small pieces imagined would be same. So this would be like each element is in parallel with the other. Suppose let's imagine dividing this into 2 parts. This is one part, one half. This is the other half. They are connected. Let's imagine the connection is separate. If I had shown you something like this, it has said, yes, I see two parallel capacitors. If this is one half and this other half, area would have been halved, this would be C by 2. If this capacitance is C, this will be C by 2, and the C by 2, they are in parallel, so C effective is C1 plus C2, C by 2 plus C by 2, that's C. That is, imagining this hasn't changed the capacitance. In a similar way, imagine small pieces which are in parallel. Now if you really had two small pieces independently without a large plate, well, the capacitance wouldn't be same as the parallel plate capacitance formula, because the fields will be affected. Let's not go into it. Well, we are going to imagine a piece of a large plate. There are other pieces also together, so if we just use two small pieces, the field will not be same as what we see here, right? Here the field starts from the positive plate, field line starts and terminates on the negative plate normal to it. So it will be very different if we had just two small pieces. These two small pieces are a part of a much larger plate, and we are considering that for calculation purposes. Anyway, you can treat one portion of the capacitor to be in parallel with the other portion. This also will be a useful idea. We have a situation like this. This is a parallel plate capacitor, and we are told one half of this is filled with the dielectric constant K1, and the other half is filled with the dielectric constant K2. This is K1, this portion is K2. So what is the capacitance now between A and B? So you can again see this portion filled completely with K1. This is filled with K1. So, and this is filled with K2. The area of the plates is A by 2. So these are two capacitors now, and these are like parallel connections because they are connected, right? Potentials are same, like parallel connection. So this capacitance of C by 2, because without the dielectric being C by 2, this will be K1 C by 2, and this will be K2 C by 2, and they are in parallel. So that will be K1 C by 2 plus K2 C by 2. So C of this system, C effective, let's say, is K1 plus K2 by 2 into C. A nice way of calculating the capacitance without having to do field and stuff like that. Each portion is in parallel with the other. Suppose we had a system like this. Half the thickness of the gap is filled with dielectric constant, say K1, and the other half is filled with the dielectric constant K2. This is d by 2 thickness and this d by 2 thickness. We learned earlier that imagining a thin metal plate doesn't affect the capacitance. So we'll imagine a thin metal plate there. So what do we have now? This is the first plate, and with that thin metal plate, we'll see the upper surface of the thin metal plate is forming capacitor with the upper plate. The lower surface of the thin metal plate is forming capacitor with. So we could imagine this the plate you imagine, this is the upper surface and this is the lower surface. So this is a capacitance of 2C, right? If this epsilon 0 A by D was C, this is half the thickness, so this is 2C. But now there is a dielectric of K1, so this becomes 2K1C. This is 2K2C, and these are in series. So 1 by C effective is 1 by 2K1C plus 1 by 2K2C. So this is well 2K1 K2C, and what do we get here? And this is K1 plus K2. So C effective will come to 2K1 K2 by K1 plus K2 into C. If K1 is equal to K2, you can see that this becomes, well, this is 2K, this will be 2K squared, K gets cancelled, it will be 2 gets cancelled, and this will be C, and KC. So, well, K1, K2 is a fully filled capacitor with a single dielectric. We have learned that capacitance goes up k times due to the introduction of the dielectric. Oh, well, this is a nice way of solving the equivalent capacitance, when capacitance of this system. And if you had to go for charges, it would be a little more tedious work. This is simpler.